My name is Gabriela Cornejo, and this is my video lab report for Lab 4, Circuits and Capacitors. The purpose of this lab is to predict the behavior of circuits containing resistors both in series and parallel. The other purpose is to use multimeters to measure values for conventional currents and the potential differences within the circuits, and to build the circuits ourselves so that we can have a better understanding and visual frame of reference of circuits and how they function. This lab had two parts to it, each one with a different purpose and results. Part 1 was to find the total potential difference across a circuit, which should be equal to 0 volts, and the second part was calculating time-dependent voltage across a discharging capacitor and finding the time constant RC, which I calculated to be approximately 6.8 seconds. The main physics principles used in this lab are energy conservation, such as using the loop rule where the sum of the potential differences equals 0, and current conservation and how resistors and capacitors function in circuits, such as the time constant RC equaling 6 seconds for this experiment. The first section of the lab was charge conservation and energy conservation in series circuits. So for the below circuit, I predicted the value of I to be 0.02 amps using the equation V equals IR, where I ends up equaling V over R, which is 3 over 147, the total resistance, which ended up being 0.0204 amps. And when you insert it backwards, it should read negative 0.02 amps because of how the current flows. We then created an open circuit with the potential difference across it being approximately 3 volts because the first reading would be 3 and the second one would be 0 because no current can flow through the open circuit. The ammeter also reads 0 amps because no current is currently flowing through the wire. We then calculated the potential difference across the circuit by calculating potential differences across various parts of the circuit and summing them up to get the total potential difference. The total potential difference ended up equaling 0 volts. The ammeter reading does not change with the addition of a voltmeter because the voltmeter only measures the potential difference in voltage. Voltmeters have infinite resistance, thus they do not change the current. The calculated resistance values using our values for R, delta V, and I ended up being the 47 ohm resistor had a resistance of 47.95 ohms, the 100 ohm 102.05 ohms, the wire had 0, and the ammeter 0. These calculated values demonstrate how our experimental values are fairly accurate when compared to the expected ones. In contrast with the voltmeter, the addition of an ammeter in parallel to a circuit does change the value of the current. The current through the ammeter changes to 0.06 amps because the circuit now has a part in parallel, and through the node rule, we know that the current will now split between this junction. The next part of the lab was about RC circuits and charging a capacitor. So as the capacitor charged, the light dimmed until eventually it stopped glowing at all when the capacitor was fully charged. The more the capacitor charges, the slower the current moves through the circuit until it eventually stops altogether. We also looked at a circuit with a discharging capacitor. So again, as the capacitor discharged, the light dimmed, and the light stopped glowing when the capacitor was fully uncharged. The current reversed in this circuit because of the orientation of charges in the capacitor, and it also slowed to a stop as the capacitor discharged. For these circuits, we completed the experiment with two different resistances. The 10 ohm resistance bulb took about 10 seconds to charge and discharge, and the 20 ohm one took approximately 20 seconds. It makes sense that the time for the 20 ohm bulb is about twice the time for the 10 ohm bulb since the resistance is twice its size. The final portion of the lab was to plot a natural log of delta V over delta V naught versus time graph using our experimental values. All of my experimental and calculated values are shown in the table below, and they're plotted to the right with the equation of the line shown on the graph. To find the time constant RC, we can use our experimental values and the equation ln of delta V over delta V naught equals negative T over RC. Using the equation of the line from our graph, y equals negative 0.1457x plus 0.082, we can solve for RC. So the slope, negative 0.1457, is equal to negative 1 over RC. Thus, RC equals 6.8 seconds. The expected value of RC is 6 seconds, so this is a fairly close calculated value. If we did this lab in real life with an actual ammeter rather than an ideal simulated ammeter, then the results for current would be lower. This is because there would be more resistance in the actual ammeter. Our ideal model would predict a capacitor to reach full charge instantly if it existed in a circuit with just a battery and no resistor. In real life, the capacitor would not reach full charge instantly because resistance still exists in the circuit even if there's no real resistor. In conclusion, this lab helped reinforce ideas learned throughout lecture on circuits, energy conservation, and current conservation. The calculated total potential difference across a circuit was found to be 0 volts, which goes along with energy conservation in the loop rule. The value of time constant RC was calculated to be approximately 6.86 seconds, which nearly matches the expected value of 6 seconds.